So today's topic is adders and subtractors, but before I get into the details of adders and subtractors, I want to talk about the general category of circuits that adders and subtractors fall under, and that is combinational logic circuits. And combinational logic circuits are simply circuits whose outputs depend solely on the values of the inputs. Now this is different than another type of circuit called a sequential logic circuit, where the output depends on not only the inputs but also the current value of the outputs. And I'll have a video for that you can watch later to cover the topic of sequential logic circuits. Now, any circuit whose output is solely dependent on the inputs is going to go through some set of logic gates. And there's some circuits that we can create that are so commonly used that we usually just encapsulate them inside a box, the circuits inside the box, and we just worry about what the inputs and outputs are. And that's something that an adder and subtractor is. Like it's a box, a circuit, a black box circuit that we give it a couple of numbers, a couple of binary numbers, and it adds those numbers together and gives us an output. But what we're going to do is figure out what goes on inside an adder and subtractor circuit. And we're going to start off looking at an adder. And what we're going to do is, first of all, figure out what is the truth table for a single bit adder. So if we're adding two bits together, we've got two single bits together. Let's call those two bits A and B. And A plus B is going to give us a sum. Actually, let's do it this way. Let's move sum over a little bit. It's going to give us a sum, and it's also going to give us a bit called a carry bit, right? And when we did binary addition, there was, you add two bits together, and sometimes you had to carry out a bit, and that's where that carry bit comes into. So this is the truth table for an adder. A, and we're thinking, remember, A is added to B, so A plus B, 0 plus 0 is going to give us 0. We're going to carry out a 0. 0 plus 1 is going to give us 1, and we carry, there's no 0. And 1 plus 0 is going to give us 1, and there's no carry. And the final possibility is 1 plus 1 is going to give us 0, and we carry out a 1. I mean, the other way to look at it is that each one of these are my additions, and then the two numbers I'm adding together, and the 2-bit output is made up of the carry and the sum. So 0 plus 0 is equal to 0, 0. 0 plus 1 is equal to 0, 1. 1 plus 0 is equal to 0, 1. And 1 plus 1 is equal to 1, 0. Just the basic rules of binary addition. But if we treat this as a truth table where we have two inputs that are creating two different outputs, we can figure out what carry is as a function of A and B and what sum is as a function of A and B. And very simply, if you look at it, when carry is let's delete these addition signs there. So if these are our inputs and this is our output, you can see that if you pass A and B through an AND gate, you'll get the carry bit. And if we look at this as our output with A and B again as our input, that sum bit is equal to the exclusive OR operation between A and B. So I've got this circuit over here. I've built it in Quartus, and this particular circuit, here's my A input, my B input, and my sum output, and my carry output. And this particular circuit is called a half adder because it adds two bits together, but it doesn't quite have all the functionality of a full addition of when you're adding two bits together. The thing that is missing is the carry in. Now normally if you're just adding two single bits together, you don't worry about a carry in, but think about it, if you're adding two 4-bit numbers together, you're going to build a 4-bit adder from several different 1-bit adders, and so each one of those 1-bit adders you're going to want to have the carry in coming into it, right? So we go back to my drawing program here, and if I'm adding two 4-bit numbers together, 0 plus 1 gives me 1, and my carry would be a 0. I can write it there. 1 plus 1, or 0 plus 1 plus 1 gives me 0 with a carry of a 1. 1 plus 0 plus 0 gives me a 1. 1 plus 0 gives me a 0 with a carry of a 1, and so I've got a carry out there of a 1. So I've got, for each one of these bits, we should be able to make a circuit. For each one of these 2-bit additions, make a circuit. And in order to make that circuit, we're going to have to include the carry in as well. Okay, so I'm going to clear my table here, and if I'm including a carry in, that means I've got 3 inputs to my truth table. I'm going to have A, I'm going to have B, and I'm going to have my carry in. I'm just going to call it C in. And then my outputs, I'm going to have the same 2 outputs. I'm going to have carry. So let's just call it C out. I'm going to carry out. And I'm going to have my sum bit. So I've got my 3 inputs. I'm looking at all my possible combinations of 3 bits. Oops. That should be a 1 there, of course. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So my 8 combinations. And then for each one of these combinations, what am I going to get for a carryout and what am I going to get for a sum? So we can again think of these as just adding the 3 numbers together to give me the 3 single-bit numbers together to give me a 2-bit output. So 0 plus 0 plus 0 is going to give me 0, 0. 0 plus 0 plus 1 is going to give me 0, 1. 0 plus 1 plus 0 will give me 0, 1. 0 plus 1 plus 1 is going to give me 1, 0. 1 plus 0 plus 0 is going to give me 0, 1. 1 plus 0 plus 1 will give me 1, 0. 1 plus 1 plus 1 will give me 1, 0. Or 1 plus 1 plus 0 will give me 1, 0. And finally 1 plus 1 plus 1 will give me 1, 1. So now I've got a new truth table, 3 inputs and 2 different outputs. So we're going to consider the logic expression for the output a little bit differently here, or separately. So we'll figure out the carry out and we'll figure out the sum. So the C out, we can use our rules for figuring out a sum of products expression from a truth table. So we look at it, all the rows where the C out is a 1, and put together the product expression. So the first one is not A, B, C, ORed with A not B, C, ORed with A, B not C, ORed with A, B, C. I guess I should be calling these C in, not just C. And with some Boolean algebra, I'll leave this to you as an exercise. We can simplify this down to C in ANDed with A XORed with B ORed with AB. Now there's a few steps we have to go through and there may be a little bit of trickiness involved, but it's something that you should be able to do, and if you can't, then you can look to somebody for some help. But it's this expression that we're going to convert into a logic circuit. And we're going to need to do the same thing with the sum. We've got 1, 2, 3, 4 rows where the sum is output is equal to a 1, and so we're going to put that together. We've got not A, not B, C for the first row here. Second row is not A, B, not C. Again, C in, should be calling that. ORed with this third row here is going to be A, not B, not C in. And finally, ORed with A, B, C in. Now we can also simplify this expression, and I'll leave it up to you as an exercise. And there's again a little bit of trickiness involved, but you should be able to simplify it down to A XORed with B XORed with C in. And with the XOR operation, you can also write this as A XORed with B XORed with C in. So we've got an expression for the sum here and an expression here for the carry out. And we can implement this in logic gates like so. Now we've got A XORed with B, and then that's XORed with C in to give us the sum. And over here for the carry, we've got A ANDed with B, and we've got A XORed with B ANDed with C in, and then those two things ORed together to give us the carry out. And I'll give you a second to compare the Boolean expression that we have with the logic circuit that we have right here. So this full adder is such a common circuit element that it's we can typically just write it like this, something like this. Here's my full adder circuit. I'm just going to write this with the Greek letter sigma for the sum operation, and it's got 3 inputs, A, B, and C in, and then it's got 2 outputs, the sum and the carry out. And inside this box is the circuit that we came up with that I just showed you in Quartus. You might see it in this orientation, you might see it flipped or rotated about 90 degrees, but this is the general idea. 3 inputs, A, B, and C in, 2 outputs, carry out. And this only does a single bit, but now these things can be cascaded together to give us whatever number of bits we want. I'm going to orient it, I'm going to flip it another direction, but each one of these boxes is a carrier. I mean, not a carrier, it's a sum, full adder. And I've got my 2 inputs, A and B. I've got the 2 bits that are being added together. I've got a carry in, and then I've got a sum bit coming out. And to cascade these things together, I take the carry out of one of the less significant bit and connect it to the carry in of the next bit over. So each one of these has my sum output. So I should call this sum bit 0. This is going to be sum bit 1. And then I got my carry out of the second bit here, goes into the carry in of another circuit, another full adder. Give me the sum bit number 3, or call it sum 2. Carry out of that goes into the carry in of the next one over. And you can see I can just cascade these things together and make as many as I want. Now the only problem with this kind of adder is that the signal, let's say we've got a B0, A0, B1, A1, B2, A2. So far we've got this 3-bit number, 4-bit number, or whatever number of bits. And so the least significant bits of the 2 numbers, A0 and B0, get added together, and then it's got to go through some logic circuitry here. So there's actually some kind of propagation delay, a few tens of nanoseconds maybe, before sum 0 is created and before sum out is created. And similarly, over here, there's some kind of propagation delay between when A1 or B1 or a C out changes before the sum 1 gets created. But you can see that there's dependency. Sum 1 is a function of A1, B1, and C out from the previous bit, and the previous bit is going to take a few tens of nanoseconds before it's a valid value, and then it's going to take another few tens of seconds before this sum bit is a valid value. So let's say it takes 10 nanosecond propagation delay for each one of these gates. So the value gets applied to the input of the AND gate of the adder. 10 nanosecond propagation delay before Cout is valid, and then it's another 10 nanosecond delay before some one bit is valid. So we've got, from the beginning, we've got 10 nanoseconds plus another 10 nanoseconds, and so we're up to 20 nanoseconds before some one is valid, and Cout will be valid at the same time as this bit. So we will be applying Cout 20 nanoseconds later, and then it's going to be another 10 nanoseconds delay before sum 2 is valid. So it's going to be a 30 nanosecond delay before sum 2 is valid. So each one of these bits in the sum is valid 10 nanoseconds later than the previous one. So this one will be valid at 10 nanoseconds, this at 20 nanoseconds, this at 30 nanoseconds. So we get this ripple effect as of the bits becoming valid. They don't become valid at the same time. And that's why this type of is called the ripple carry adder. And now there's other ways of designing an adder circuit to create a faster summer, so that it sums the bits, and each one of the bits, sum 0, sum 1, sum 2, sum 3, etc., are all valid at the same time, and only a 10, 15, 20 nanosecond delay for all of them to be valid. But we're not going to get into that kind of adder in this video. The last thing I do want to show, though, is how to make a subtractor. Now, when we did binary arithmetic, or when you looked at binary arithmetic, hopefully you can remember that I said subtraction is the same as adding the negative of a number. So if we build an adder where part of the adder is making the negative of one of the inputs, we can make a subtractor circuit. So let's look at how that can be done. So right, if you have two numbers, so, well, it's just like in decimal form, two numbers, 10 minus 3, that's the same as saying 10 plus negative 3. So if we can have a circuit that we apply, let's call this number A and this number A and this number B. So A gets applied to here's my adder circuit, and is my adder circuit, and overall we're trying to make a subtractor circuit. So B will first go through, let's call it an inverter, more like a negator, I guess. So the number 3 gets passed through this inverter, and we're going to have A plus negative B to give us A minus B. And in binary form, the negation, this inverse property, or this inverse operation, is going to be doing the 2's complement operation on that number. Typically, it could be the 1's complement operation if you're dealing with 1's complement signed number system, but most number systems in computers are 2's complement number systems. So passing B through a 2's complement operation is going to give us negative B. Now let's clear this and look at how you would do a 2's complement number system. Remember, 2's complement is you invert all the bits and then you add 1. So I guess the best way to see this operation is to look at an example. So let's have two numbers. Let's call these A and B, two 4-bit numbers, and we're going to subtract one from the other. So let's go A is 0, 1, 1, 1, and let's say B is equal to, so we got A minus B, so 7 minus, I don't know, when we subtract a bigger number, 7 minus 8. Can we do 8? No, we can't do 8 in 4 bits. 7 minus, let's just do 6. 7 minus 6. So that's the same as A plus negative B. So A hasn't changed, but in order to get negative B, we're going to have to do the 2's complement operation on this. So 2's complement operation, we flip all the bits, and we add 1. So 7 minus 6 is the same as 7 plus negative 6. So if we were to add these two together, 0 carry the 1, 0 carry the 1, 0 carry the 1. Remember, when we carry in 2's complement addition, we don't worry about the carry out of the last addition. So 7 minus 6 is equal to 1. Makes sense. Now, how do we do this in logic circuit? Well, let's say we've got just have a 4-bit adder here. And inside this 4-bit adder is just going to be four single-bit full adders, where we've got the carry out of the least significant bit going into the carry in of the next bit. But just to save some writing, I'm not going to write them all. So we're going to have A3, B3. A3 goes straight in, but B3 gets inverted. A2, B2, A2 goes straight in, B2 gets inverted. We got A1, B1, A1 goes straight in, but B1 gets inverted. And I made my adder a little bit too small. A0 and B0, A0 goes straight in, B0 gets inverted. So that does the inversion of all the bits. In order to get the adding of 1, we're going to make the carry-in of the least significant bit equal to a 1. So that means that the first full adder here will always have 1 added to it, and that's going to do our operation of the 2's complement, inverting the bits here and adding 1. And we're going to have, let's call this D3, D2, D1, and D0, where D just stands for the difference. So this if this is a 4-bit full adder here, this overall circuit is going to give us a subtractor. Hopefully that all makes sense, and we will be looking at a couple of more of these combinational logic circuits that are used so commonly that they're typically just given a black box where the logic inside is so standard that we don't usually have to worry about it, except that I'm going to show you what that logic inside is.